Good morning, everybody. So let's pick back up in chapter 4. So we were talking about this ionization process last time. So we're talking about how when things like NaCl dissolve in water, they ionize completely into their cations like Na plus and Cl minus. Other compounds don't necessarily do this. Like methanol, a molecular compound, turns out to not ionize at all when it goes into solution. We also saw an example of sucrose, where sucrose didn't ionize as well. And so when we're thinking about the properties of substances in solution, we can come up with a couple generalities. One is for ionic compounds. And so one thing I wanted to talk about today or start off with is that all water-soluble ionic compounds. We're talking about ionic compounds, and we're talking about specifically the ones that are water-soluble. We can think of our solubility chart that we showed last time. For all those compounds that are water-soluble, those compounds are strong electrolytes. And that just simply means if the compound is water-soluble, then it ionizes. Then it breaks up into its individual ions. So if we have a mole of sodium chloride in water, we would have 6.022 times 10 to the 23 sodium ions, each one individually surrounded by a little water sphere. And we'd also have an Avogadro's number of chloride ions, each one of those ions individually surrounded by a water sphere. So you end up with these ion spheres of the plus and minus spheres kind of floating around solution. And then we can contrast this. I just want to make sure we contrast this with molecular compounds. That molecular compounds can actually be strong electrolytes, they can actually be weak electrolytes, or they can actually be not an electrolyte at all when they're in solution. And we also don't really have an easy way of predicting solubility or miscibility. So for molecular compounds that are either soluble is usually a term you think of a solid as being soluble or insoluble, or miscible. Miscible is usually a term you think of a liquid as either being mixing with another liquid or not mixing with another liquid. But molecular compounds that are soluble or miscible in water can be strong electrolytes, weak electrolytes, or non-electrolytes. And just to give a couple examples, we were looking at a few of these last time, that a strong electrolyte could be something like HCl, a strong acid. So we saw a solution of HCl was able to light up that light bulb last time. So strong acids are molecular compounds that, when they're in water, completely dissociate into their ions of H plus and Cl minus in this case. We saw an example last time of acetic acid not really lighting up that light bulb very brightly. That's because it's weak. It's just a partial ionizer. So our HC2H3O2 is an example of a weak electrolyte. This is what we call a weak acid. We also saw NH3 was a weak base that did this as well. So NH3 was partially, we'll talk about the reaction a little bit later today, but NH3 partially reacts to form some ions, in particular hydroxide ion. And so it behaves as a weak base, weak electrolyte. And then pretty much everything else, our non-acids and bases, fall into the category of being non-electrolytes when they're in water. And two quick categories of compounds that are generally soluble in water or miscible in water are alcohols and sugars. There's a lot more examples than those, but I mean, just for examples of things that we've seen a fair bit in the class, those are some compounds that when we mix in water, we can know that they're not going to ionize in an acid way or a base way. All right, let's talk a little bit more about acids. Let's talk a little bit more about bases here today. And sorry, my slide doesn't want to advance. All right, so I don't know. I had to like stop recording and to change slides. Okay, so getting into acids and bases and some of their reactions is section 4.3. And so we were getting into the topic last time of identifying things like HCl. We identified was a strong acid. I think we saw a slide that showed HNO3 and H2SO4 were also strong acids. But we see here the list of 7 strong acids. And this is a list that we do have to kind of put to memory. That HCl, HBr, HI. So most of the halide acids are strong acids. You might notice one of them that's not listed is HF. HF is in the category of being a weak acid. So when we're thinking F, Cl, Br, I, let's make sure that we pick out HF as being in the weak category. And that just means that something like HF in water is a partial ionizer to H plus and F minus. And so that we just don't get 100% yield, we get an equilibrium on that reaction. Whereas something like HBr, HI, HCl, these things here go to 100% completion. Now, I mentioned this before, and I'll mention it again, just because HF is probably one of the most nastiest chemicals you could possibly work with. Don't think HF is safe to work with just because it's a weak acid. It is actually much more hazardous than HCl, HBr, HI. And also don't take that to mean that working with strong acid like HCl isn't something to wear safety goggles with, lab coats, gloves, and that variety. So strong acids, strong bases can burn you. HF can do a lot worse than that. So avoid this if you can in the lab. But so HCl, HBr, HI, 3 strong acids, also HNO3. Then we got our chloric and perchloric acids, HClO3, HClO4. So notice we don't see HClO or HClO2. We also don't see like bromic acid or perbromic acid, or the like the iodic acid isn't on this list either, just HClO3, HClO4. And then we also had talked last time about the first H falling off of H2SO4 is strong. So when we look at H2SO4 in water, it would be 100% dissociated into these ions here of H plus and HSO4 minus. So hydrogen and the hydrogen sulfate ion. And then HSO4 minus, this ion here, does a partial and equilibrium decomposition into the second H plus falling off. So we get a little bit of sulfate ion, mostly HSO4 minus in solution, and some H plus ions. And so all of our strong acids are ionizing, right? So we're certainly ionizing. 1 mole of these acids is turning into at least 2 moles of anions and cations, and H2SO4 a little bit more than even 2 ions. And so then our weak acids are not quite getting to 2 full ions in solution. So we get a partial ionization for HF. So the implication would be something like HF would light up our light bulb a little bit, but not very brightly. Same thing with HNO2, acetic acid, phosphoric acid, sulfurous acid. We could really go on. All the other acids we learned how to name in chapter 2, we could take for granted here and say that if they're not one of those 7 strong acids, then we know that that acid would be a weak acid. It would just do a partial dissociation in water into H plus and its counter ion. Now, the counter ions are a little bit complicated in what they do in water. Like when you have certain counter ions in water, they can react with water. You go into some of those reactions in chapter 16 later. But they generally don't fall apart. So we've talked about this before, how sulfate or nitrate tend not to fall apart into like sulfide or nitride ions, oxide, things of that nature. So picture these molecular ions as staying intact when they fall into solution, just like we pictured for things like when K3PO4 hits water, that the phosphate 3- ion would form, and it's not going to fall apart into like phosphide and oxide or anything crazy like that. And then lastly, let's look at some examples here of things that aren't acidic or basic. So those would be things like CH4, which isn't particularly soluble in water, but water itself is only a partial dissociator. you know probably the pH of water is 7, so you get a concentration of H plus in water of 10 to the minus 7 moles per liter. Tiny, tiny fraction of dissociation of water, not enough to really call it a weak acid. We tend to think of things as being weak acids of things that are almost more acidic than water. So when things are more acidic than water, tend to be the cutoff for things that we start to think of as acting as acids in water. And so then we have methanol, ethanol, the alcohols, sugars, etc., are not acidic, not basic. Anyways, so let's also classify acids as whether or not they have 1 H plus to donate, 2 H pluses to donate to a solution, or 3 or even more. So a monoprotic acid has 1 H plus that can fall off into the solution. And it doesn't matter if the acid is weak or strong here for us to call it monoprotic. Like we would call HF a monoprotic weak acid. We might call HCl a monoprotic strong acid. So monoprotic is just more along the lines of how many H pluses could possibly fall off of that anion into solution. For HF and HCl, HNO2, just 1 H plus. For diprotic acids, again, it doesn't have to be a strong acid to be diprotic. It's just having 2 available H pluses to leave behind that ion that we recognize, like carbonate. We can lose 2 H pluses off of H2CO3, so it's also diprotic. And then something interesting to kind of then make sure that we see is that when we get to like H3PO4, of course triprotic for H3PO4, but for citric acid, you see all these H's here that just remain intact. Like those CH bonds are very strong. They're not going to break, but these are the acidic hydrogens. These are the H's that look like that functional form for acetic acid. If you recall, we sometimes write it like this. It's that COOH group that's acidic. So these are the 3 acidic hydrogens on acetic acid. Those are the 3 that could fall off. We'll see that if you add maybe hydroxide ions, something to react with those H plus ions, we can pull all those off the molecule. Even if they don't fall off in solution automatically because citric acid isn't a strong acid, if we add hydroxide ion, if I add 3 sodium hydroxide ions to a solution of citric acid, those hydroxide ions are going to pull those H pluses off, but only those H pluses over here. They're going to leave these H plus ions here. They're going to leave these hydrogens alone. They're not going to take those hydrogens, so those stay put. Those bonds are too strong. But these ones are weak enough for the hydroxide ion to take. So if we did the citric acid reaction with sodium hydroxide, we'd be forming 3 moles of water by taking off those H pluses here and pairing them up with the hydroxide ions, and then we'd have our 3 carbons in sequence, and then the COO minus, from losing the H plus, and then all these other hydrogens are still intact. And then our sodium plus is just the counter ion here. So we'd be forming, that would be sodium citrate, is what that structure is. And so the structure is just the H pluses being removed, minus charges being left behind, and then sodium plus balancing out those charges. Now this should be, if we were to ask sodium citrate, water soluble or insoluble, and how do you know? It's aqueous because everything with sodium ion is water soluble. So you take an alkali cation, any of the first row cations paired up with any other anion have to be water soluble. So that kind of will get us into our topic of acid-base reactions, which we're going to talk about in just a moment. Okay, so before we get into writing acid-base reactions, let's talk about, bases. We'll talk about strong bases and weak bases on this slide. So strong bases turn out to be strong electrolytes in water by definition, because a strong base is anything that releases hydroxide ion. And if you think about our solubility rules, we know a bunch of ionic compounds that release hydroxide ion into solution. We have all of the water-soluble exceptions for hydroxide ion. So we have things like ammonium hydroxide. Pair that up with hydroxide, that's water-soluble. It's an ionic compound. Ammonium is a weird one where it's not a metal cation. Usually we look for ionic compounds being metal cations paired up with anions. But this is a molecular cation, molecular anion, we do have an ionic compound here. This thing in water would form NH4 plus and hydroxide ion. So ammonium hydroxide would be a strong base because we're making hydroxide ion. And then the other ones are the alkali hydroxides, of course, which are water soluble, so like sodium hydroxide. Sodium hydroxide in water would be sodium plus and OH minus. And so this would take place to 100% yield, again, because this is a water-soluble compound. It's an ionic compound, and it's therefore a strong base because it's specifically releasing hydroxide ion. So we'd have all the other alkali cations, and we'd also have the 3 calcium, strontium, barium alkaline cations that can pair up with hydroxide and be water-soluble, like calcium hydroxide will form calcium 2 plus 2 hydroxide ions. Last time I was talking about yield, maybe it's a little confusing if I'm thinking of yield of reaction. Sometimes I was writing at 100% yield. Any of these like quote-unquote strong reactions, the implication is that that reaction is taking place to 100% yield. So we're getting 100% ionization. Anytime I might be writing in or using equilibrium arrows, that's to imply I'm not getting 100% dissociation or 100% reaction. I'm getting, maybe some partial, maybe 1 to 10% or so reaction to take place to form products. But here I'd get 100% dissociation. So calcium hydroxide, again, a water-soluble ionic compound because it's releasing hydroxide ion. It's a strong base. So it's also a strong electrolyte. So these are all all these terms kind of apply. It's like the thought of, is it ionic? If it is, we can predict water solubility. If it is water soluble, we know it's ionizing completely. And if it's ionizing to hydroxide ion, then we're calling it a base as well. So we have all of those water soluble hydroxide exceptions. Now there are a variety of other things. I used to teach this more, but I think I'll just leave it as a general example. If you have like sodium oxide and that hits water, it should fall apart into oxide. Oxide will pull an H plus off of water to make hydroxide. So there's a variety of things like sodium oxide. There's a variety of anions that so strongly react with water that they produce hydroxide ion, leaving behind that hydroxide ion off of water. We can even write this out real quick just to think of what I'm saying in terms of a reaction. So we get this reaction here to form the oxide ion. Then oxide ion, because this is in water, has plenty of water available to do this next reaction where it forms the hydroxide ion. So it's pulling an H plus off and leaving behind the hydroxide ion. So let's even write this as H here and then hydroxide so that you can see it's pulling the H plus off and it's leaving behind the OH minus. So we're actually forming 2 of those hydroxide ions in this process. And so the oxide ion, and I don't think this would ever be on the test or anything, but the oxide ion itself is a strong base because it's completely reacting with water to form hydroxide ion. And so this here is a strong base. Sodium oxide, you can also, therefore, because it contains that oxide ion, call it a strong base in water. So there's a lot of behavior that some anions can have in water that's kind of challenging to understand. It requires us to think about a lot of different equilibrium processes or reactions with water. We're not going to address most of those reactions here in chapter 4, but I think this is a good example of why, when you look at your solubility chart, if you've ever wondered why are there, only 10 or so ions that are shown in the solubility guidelines chart, what about all the other anions we learned about? The issue is that they're complicated, that they have a lot of these complicated side reactions that can go on in water that we should either talk about or maybe just not even talk about oxide solubility rules so that we don't get into these complicated side reactions. I just wanted to point out that there's a lot of other things that are strong bases, not just hydroxide containing salts, but a lot of those you won't touch again or talk about again until Chem 1220 down the road. Okay, so let's basically for this class, what we're recognizing as a strong base are just hydroxide containing water-soluble ionic compounds. So those are from our solubility chart. And then in the case of weak bases, there's really just one prototype, and it's a little bit hard to even build from this prototype into other types of weak bases, but ammonium is the one, or excuse me, ammonia. So ammonia is the one. This thing here reacts with water. We saw this last time where we had a solution of NH3 in water, only dimly lit up the light. And so what's happening here, we're pulling that H plus off of water, leaving behind hydroxide. So we're forming NH4 plus and then hydroxide ion as the byproduct. And just we're getting an equilibrium here. And so we get an equilibrium, only a partial formation of ions. So therefore we look at NH3, say it's partially ionizing, so it's a weak electrolyte. It's ionizing to hydroxide ions, so we also can call it a weak base. And it's not so much water solubility that we're predicting here or using. For molecular compounds, we're never really asking the question, is NH3 soluble in water? Well, presumably it has some solubility in water. So the reason why this is going on is because we have this compound in water. So there has to be something going on with water, but we're not really ever going to give you a molecular compound. I'm never going to say like some big alcohol, like pentanol. Is that water soluble? That's not something we're going to ask. What we might ask, though, is if it is in water, do you think that it's dissociated into some H plus or hydroxide ions? The answer is no, that it's an alcohol, not an acid or base. So it's kind of circular at this point that we try to recognize the acids as the things we learn how to name as acids, so that when we see the things we learn how to name, we know they're acids. You see how that's just like completely circular reasoning. But that's all we have at this point to go on in terms of predicting acid behavior. So if we don't recognize something as being an acid from chapter 2, then it's not an acid. With the maybe small exception like the citric acid, where we're recognizing that COOH group. But that's probably the extent of us recognizing a like organic style functional group in terms of acid-base behaviors, just looking for things that look like acetic acid. In terms of bases, the main example of weak base is just ammonia, or where you have like N with 3 things attached to it, like where maybe that's an R. So like an example might be NCH3, but this starts to get a little tricky for you guys to conceptualize on what that even is until we get to like sketching Lewis structures in chapter 8 and 9. So you can see things like trimethylamine is what that's called. So like amines in general are weak bases, but we usually don't go into those examples here because it's really like the real thing you're looking for is a nitrogen atom with a lone pair of electrons attached to it. And like we don't have the tools yet to be able to look at a structure and tell if it has nitrogen with a lone pair of electrons until we get the structure. So there are other examples of weak bases. They're a little bit hard for you guys to see and understand at this point. So I want to mention that there are other weak bases, hard to predict, but ammonia is really our prototype. So really just one weak base that we can recognize and easily identify at this point in the class. So pretty much if there's a weak base question, it's probably NH3. Okay, so let's try to identify here which group of compounds are all weak electrolytes in water. So I want you guys to take a minute or two to try to figure out which group of compounds where every compound in the group behaves as a weak electrolyte in water. So one way I can think to start this problem would be to first eliminate or look for in the options like the ones that are strong electrolytes, like in B. HCl and HBr are strong acids, those are strong electrolytes. HClO3 is a strong acid, strong electrolyte. What else can we identify? So we're looking for weak electrolytes. I can also then roll out the sugar and the alcohol because those are non-electrolytes. And then what about MgOH2? For some reason, this one is always confusing the classes on how do we classify magnesium hydroxide. If you go back to hydroxide ion solubility rules from the solubility chart, the soluble hydroxide containing ionic compounds are ammonium, alkali cations, calcium, strontium, barium. Magnesium is not an alkali, it's an alkaline cation. So this is not one of those exceptions. So this is insoluble. So if it's insoluble in water, we're imagining that it doesn't dissociate at all into water because it's insoluble. And so then NH3 was a weak electrolyte, HF's a weak electrolyte, but not MgOH2. So then we get to NH3, HNO2, H3PO4, those are all weak electrolytes. So those are all, 3 of them being the partial ionizers in water. I keep having to stop recording, and I'm going to forget to re-record on the next slide. Okay, so acids and bases. This summary chart is at the sort of end of section 4.3. I think this is probably one of the most confusing tables in the book, so let's try to carefully go through this. This is for classifying electrolyte type for water-soluble compounds. And that's like a really key detail, is that when we're looking at this chart, we're assuming that all the compounds that we're looking at in this chart are fitting into the category of being water-soluble. So when we think of a water-soluble ionic compound, the only possibility is that it's a strong electrolyte. You know, there's no weak electrolyte example of an ionic compound. It's either water-soluble, completely ionizes in water as a result, or it's insoluble and doesn't ionize at all, it's not in the solution. And it's not even applicable to call it any kind of electrolyte. So if you notice, there's no non-electrolyte examples, and that's because if the ionic compound wasn't water-soluble, it's just not even applicable to think about the electrolyte behavior, if that makes sense. We're trying to describe the thing in the solution, things not in the solution, it doesn't get that term. So ionic compounds either completely dissociated in water because they're water-soluble, or just at the bottom of the test tube, stuck together, frozen in their solid form. And then molecular compounds, like we were mentioning on that opening slide, were either in the category of being strong electrolytes, weak electrolytes, or non-electrolytes. Strong acids fit into the category of being strong electrolytes because they completely dissociate to H+. And this is, again, kind of making sure that we picture that HCl is a molecular compound. Sometimes we get confused and think it's ionic because it contains or can release ions in solution. But HCl is a molecular compound. This means that HCl exists as a molecule with a distinct bond between H and Cl in a way that sodium chloride doesn't do. Sodium chloride is always Na plus Cl minus. That's why we call this thing at all times an ionic compound. HCl, because of the shared electrons, is a molecular compound. But now, when you look here, you get confused because you're like, where are the strong bases, right? You might be looking at this chart saying, where are the strong bases? Well, they're here because they're ionic compounds. So the strong bases are included in the category because they're ionic compounds, and the ones of those that are water-soluble fit the category of being strong electrolytes, strong bases. So they're already in that category for ionic compounds that are water-soluble. Then our weak acids and weak bases fit the category of being weak electrolytes. So HF, HNO2, H3PO4, NH3, NH3 kind of being the only good example of a weak base at this point too. So ammonia being the best example there. And then any other molecular compound that's soluble in water is fitting that category as being a non-electrolyte, just being something that doesn't ionize at all in water, but can still be in water, like methanol can mix with water. It just doesn't turn into plus and minus cations. And I think the thing that's always good to come back to is when we're looking at acetic acid, that it's like this whole group here is what allows that H to be acidic and to fall off in water. And that's what allows this thing here to be named and called acetic acid and to behave as an acid in water. And then methanol, do you see how like it looks almost like CH3COOH, it's just missing a C and an O, but it's a very important C and O. And so this is not an acid at all. So that hydrogen remains attached to the oxygen atom in water. And then also, I like to come back and make sure that we see the CH3 in the hydroxyl group. You may think, does that hydroxyl group fall off? No, it doesn't. It's too strong. That bond that holds that alcohol group on is too strong to break in water. So it's not an acid or a base. So I think it's good to come full circle, look at a structure, and then see that just because something has the hydroxyl group and it's water soluble, it doesn't necessarily mean it falls off. It only falls off if it's attached to a metal cation or ammonia. All right, let's get into the business of writing some reactions for acids and bases reacting together. So the main acid-base neutralization reaction is that if you take a salt, which is really just another word for an ionic compound. So a salt or an ionic compound plus water will be formed as the products of an acid and a base reacting together. Take an acid plus a base, we form a salt or an ionic compound plus water. So an example would be we take HCl plus KOH. We're going to form water. So the H plus and the hydroxide ion combine to form water. And then we get the KCl as our salt. KCl is obviously water soluble, so we get KClAQ as our salt plus water. Now, if we're writing water in here, we'd write just liquid because it's going into that liquid phase, the solvent of the reaction that this reaction is taking place in. So we get liquid here. Let me even rewrite that just to be clear that we're writing water in the liquid phase. And then KCl in AQ phase. Water is like the precipitate in the metathesis reaction. We have to form something in an exchange reaction. For exchanging plus and minus ions, we have to form something that doesn't back dissociate into the reactants. And so when we form water, water forms that strong bond between H and O, doesn't break, stays intact, and drives this reaction taking place. And essentially, this reaction takes place at the speed at which H plus and hydroxide just bump into each other. So as fast as those ions can collide, they react. Okay. And so they react very quickly. We form water because it never goes backwards, or very rarely doesn't go backwards into the reactants. And so then we can also do this reaction very quickly. If we have a weak acid, this reaction takes place readily, and we can pull off the H plus even from a weak acid. So we have a strong acid, strong base. We can even have a weak acid completely react with a strong base like KOH. And then we would form, again, the salt here would be KF. And then water as the product, the other product. And it's, again, the formation of water that's driving this reaction to take place. And this reaction here takes place to just the same yield as the one above it, 100% yield. If we're writing these full reaction arrows, then you know the reaction will take place to that 100% yield and isn't one of those that's limited. I only want to point out that detail because you might be thinking, does the weak acid completely react with the strong base? And the answer is it does. And so every one of those acidic hydrogens will fall off. So in the case of HF, just one of them, with the reaction with the strong base. There's a very interesting question of a weak base plus a weak acid. How much product forms? That's a chapter 16 question you'll see later. And there you have to know how strong is the acid in acid, how strong is the base of a base, and it's a matter of which one wins out in terms of the equilibrium. It's a kind of an interesting question when you get there, but it's not one that we have the tools to answer right now. So when you have ammonia plus one of these weak acids, how much do we get 100% conversion to products? Hard to know. That's something you come back to later. Okay, let's look at a couple more reactions. So what about our triprotic H3PO4? We can react this with KOH, and each one of these H pluses will fall off. You can do this in what's called a titration. You may do this in the lab, where if you start with the acid, you can slowly add the hydroxide. You can actually go through like 3 different equivalence points for pulling off each one of those H pluses kind of one at a time. Or you can just imagine that we're going to just form the salt by adding an excess. So if we know we're going to add an excess of KOH, we have plenty of it around, we can form K3PO4, pull off all 3 of those H pluses, and form 3 waters. So H3H2O. So we have 3 of the H pluses. So we're going to need 3 KOHs to give us the K3 PO4 3 minus. Still water soluble. We could form an insoluble salt here, perhaps, depending on the choice of a base that we're using. If we use like calcium hydroxide here, we could have formed calcium phosphate, which could have been a solid. So you don't have to have salt water soluble. It just depends on the nature of the compound we're making. And then, again, we have 3 hydroxide ions pairing up with the 3 H pluses to get the 3 waters. And then the last example would be, well, what if we take the strong acid plus the weak base? This should react completely just like the opposite weak acid, strong base. And so here we're going to form NH4 plus. So this is an interesting way to think. If you remember before I said nitrogen, like having lone pairs, the lone pairs, this is a very organic thing to do. In Elchem, they start doing this a lot, where you find electron pairs, they kind of like attack, they like to use this vocabulary that these electron pairs go looking for charge. They're negative charge, so it makes sense to go look for something positive. So they pick up that positive charge, form NH4 plus, and then leaving behind Cl minus. So we're going to form ammonium chloride here, either NH4AQ, Cl-AQ, or we could even just have written this as NH4Cl AQ, where we know that that's a water-soluble chloride. And again, going to 100% yield, just anytime you have something strong with another strong or a strong with a weak, we're going to get the full reaction taking place. Let's look at a few reactions where we have the formation of H2CO3, which is an interesting acid. So if we take calcium 2+, carbonate 2-, we can pull 2 H pluses off of HCl, and then we're kind of making H2CO3, carbonic acid. Well, carbonic acid is actually not stable in water and decomposes readily when it's formed to CO2 into water. So you can imagine that we were trying to almost make the acid H2, or maybe momentarily made H2CO3. Once it's made, it falls apart into CO2 and water. And then CO2 floats away. If one of your products floats away, you can never go backwards. That's a very easy way to drive a reaction to taking place. So we can form a solid, we can form a liquid and water to drive a reaction take place, or a gas that floats away is very helpful too. And so then the byproduct here would be the chloride ion and calcium. So calcium chloride's our salt. I doubt that you'll have to memorize this reaction, but the idea here is just we're forming a gas that floats away and like would leave the reaction and make it impossible to go backwards. So we're just seeing how gas formation can help a reaction take place, just like solid formation for metathesis, just like water formation for our normal acid-base reaction. If we have hydrogen carbonate or bicarbonate ion, it can grab another H plus off of something like HBr, and then we also again form H2CO3, which readily decomposes to water and CO2. And CO2 floats away. Something that's just completely an aside, but CO2 is absorbed by water, and when it's absorbed by water, it makes HCO3-. HCO3- releases an H plus ion, which increases the acidity of water. So you leave water out on a benchtop, or say an ocean where there's a lot of CO2, or some CO2, that's perhaps increasing over time, but the oceans absorb the CO2. I've heard that, oh, don't worry about CO2, the oceans absorb it. And I then say, well, but it increases the acidity of water. Do we want to increase the acidity of our oceans necessarily? Probably not. But then also, we had CO2 in the atmosphere before, so there has to be some equilibrium. You know what I mean? It can't absorb it all, otherwise there never would have been any CO2 to begin with. So we can never get back to what we had before just with that one process. So I like to think a little bit as we go along on how different sort of like world events, like in terms of like, say, climate change, CO2 increase in the atmosphere from man-made sources, how they can't just be rectified by natural sources where there already was an equilibrium that was established before. So just a quick aside on if you imagine CO2 above water, forming HCO3-, we can actually acidify water from the presence of CO2. But that's neither here nor there. Just a very quick, here is just the HCO3- forms carbonic acid, decomposes CO2, floats away, reaction takes place. So one last reaction is a sulfide ion reacting with sulfuric acid, where we're pulling the 2 H pluses to react with the sulfide ion. Here we would form H2S, smell like rotten eggs, not a pleasant smell, but this would evolve from the reaction, float away, and then would help drive that reaction to taking place. So we can form a salt plus a gas as well in a acid-base reaction where we're not looking at just the acid, the H plus containing acids and the hydroxide containing bases. So still acid-base reactions, a little bit more complicated, but here it's just really seeing that the gas formation is driving these reactions to taking place. So one last thing to talk about is to get maybe like a net ionic reaction from a reaction. Let's look at that K3PO4 formation where we had H3PO4 when we had this reaction before, plus KOH. We had 3 of them, if you recall, AQ, forming K3PO4 AQ plus 3 waters. And so let's say we have this question or this issue. Can we write a net ionic reaction? And can we identify spectator ions? And can we write that net ionic equation or the net ionic reaction? Now, the reason why I want to think about this is it helps me imagine what I'm really trying to think about here is I try to break apart my strong electrolytes. So I ask the question, is the reactant a strong electrolyte? Because if it is, it's ionized on the reactant side. And if it's not ionized. So H3PO4 is a weak electrolyte, so it's not a strong electrolyte, so it doesn't completely ionize. So I just write that as H3PO4 and not as 3H plus PO4 3 minus. Now let's contrast this with my product where I ask the same question for K3PO4. Whoops. Is it a strong electrolyte? And it is. So on the product side, I'm writing 3K plus PO4 3 minus for K3PO4. So again, it's a strong electrolyte. I ionize it. It's an ionized form in the reaction. KOH is a strong electrolyte. So it completely dissociates into 3K plus 3 hydroxide ion. Now what about water? Is water a strong electrolyte? Of course not. And so water just stays intact as 3H2O. So we dissociate the dissociators, we dissociate the strong electrolytes in our reaction to get the full ionic reaction. So this reaction here, this is the full ionic reaction. That's like a full glimpse at the ionic level or the molecular level, what's going on in this reaction. If you recall, this version of the reaction here is our full molecular reaction. Now, full molecular just means we're writing things like they're molecules even if they're not. Like K3PO4, AQ doesn't exist that way in water. It exists as 3K plus and PO4 3 minus, but it's very colloquial and very common to write this. It's very helpful still to write that. We just have to think it's really K plus and phosphate ion in solution. It's really this. And then to get our net reaction, if that's our full reaction, to get the net reaction, we just identify what isn't changed on both sides. So what's exactly the same on both sides of the reaction? The K plus. So the K plus is our spectator ion. And it's the only spectator ion here. And so then we can cancel it out to write our net ionic reaction. So the net reaction would be H3PO4 AQ plus 3 hydroxide ion goes to PO4 3 minus plus 3 waters. I'm just going to throw the AQs in. Any ion is always AQ. So sometimes when I have a plus or minus ion, I don't write the AQ. But of course it is water soluble. So H3PO4 AQ, 3OH AQ forms PO4 3 minus AQ plus 3 liquid waters. And so this reaction here is the net ionic. Now, to be fair, I don't really understand why it matters to write these different reactions, but I think it's helpful to think about the molecular is probably the easiest to write, and it's also going to be the easiest to use when we get into solving stoichiometry problems. I think this reaction is probably the most useful to write and to balance and to use for problem solving. This one here, I think, is the best one to think about for what's actually going on in the reaction. That's the actual picture of what's going on at the molecular and ionic level. And then the net change is just the net version of that reaction. So sometimes this reaction down here, you'll see this as summary reactions written this way, where they'll give you kind of the net ionic reaction in the table sometimes for tables of data. And then sometimes you'll see this maybe to help you solve other types of stoichiometry problems where solving it this way might be a little bit more helpful. So let's identify here the strong electrolytes in water. So strong electrolytes in water are either strong acids or water-soluble ionic compounds. So what about KOH? Is that water-soluble? Yep. Is it ionic compound? Yep. And so therefore it's a strong electrolyte. Is that a strong electrolyte? Acetic acid? Nope, that's a weak acid, so that's a weak electrolyte, not a strong electrolyte. That's a non-electrolyte. Now, PbI2, sometimes a little confusing. Is that water-soluble? Insoluble, so it's not a strong electrolyte. So only KOH here is the strong electrolyte in water. So let's just skip a couple slides ahead. And in a way, section 4.4 is a strange section. It kind of gets into oxidation numbers and predicting oxidation reduction reactions. Like section 4.5 kind of continues along into 4.6 from what we were just talking about pretty nicely. So I'd rather get through the solution problems we need to solve and then come back to that section 4.4 afterwards. And so let's get into talking about concentrations of solutions. Some of these things are pretty easy to comprehend, I hope, that we could put into practice some problem solving that looks just like problems we solved in chapter 3 when we looked at chapter 3 stoichiometry. So molarity, when we see 1.25 m CaNO3 what this means, what capital M means, is moles of the solute per volume of solution. And let me even write out solution, just so we're clear. So volume of solution, moles of the solute. And so 1 m would mean 1 mole per liter of that solution. So we maybe prepared a solution where we put 1.25 moles of calcium nitrate. Imagine you put that number of moles into a flask and you fill the flask as you're dissolving the compound up to a liter. And I think we're being careful here to talk about the difference between the solution volume versus the volume of maybe water it took to mix together. Who knows how much water it takes to mix together with this quantity? We just know what we want to know is the total volume of the solution, because where we're going to use molarity is if I have 25 milliliters of this solution, how many moles of the compound was delivered? I can easily do a conversion of volume molarity units to tell me how many moles were delivered. We'll talk about that calculation in a minute. But molarity is just moles of the solute per volume of the solution. So 1.25 m of CaNO3 has this meaning, that it's 1.25 moles calcium nitrate per liter of the solution. And so let's just say, for example, before we move on, you had 25.0 milliliters of that solution. If you had 25 mils of that solution, all we really need to do here is then multiply this molarity by 0.0250 liters. So just convert 25 milliliters to liters. So if we take 1.25 times 0.025, that gives me 0.03125 of the calcium nitrate. So I can easily just take a volume and a molarity and know how many moles of the solute are in that solution. So that's the power of molarity. It's kind of like the molar mass in a mass. If I give you a mass and a molar mass, we can get moles. If I give you a volume and a molarity, you can also get moles. And let's also then talk about the concentration of the electrolytes in the solution, because the solution really doesn't contain any calcium nitrate, right? Like calcium nitrate isn't paired together, water-soluble ionic compound. So we might write this. What is the Ca2 plus in brackets? The brackets imply what's the molarity of what's inside of it. So what's the molarity of calcium 2 plus in the solution? Well, calcium nitrate contains 1 mole of Ca2 plus. So if we're looking at this solution here, 1.25 molar, it's 1.25 moles of calcium ion per liter of solution. So it's 1.25 m, capital M, calcium ion. So that's just moles per liter. Nitrate ion, the molarity of nitrate ion I'll write this out, even though it's probably pretty obvious, but we're just starting with the moles of calcium nitrate in that solution that we know is in there, and just using that 1 mole of calcium nitrate contains 2 moles of nitrate. So of course that's 2.50 moles or molar nitrate. So the vocabulary usually goes molar, but this is 1.25 molar calcium nitrate, so it's 1.25 molar calcium, 2.50 molar nitrate ion. Well, where we're going to eventually get to is using the concentration unit of molarity in stoichiometry problems, where we can look at reactions and quantify what's going on in reactions using this like a molar mass and mass, but with volume and molarity. All right, we'll pick up from this problem next time, get through the rest of chapter 4, circle back to section 4.4 after that. Have a great weekend, guys.